lithium-ion battery simulation. And in this talk, I will present more thoroughly the meshing app I did, which allows me to do all this importation and then simulation into commercial softwares. So at first, just a quick overview of my short career in battery. So I'm a second-year PhD student at the LRCS in France. And before that, I did a few months in internship in the University of Surrey with Dr. Kyung-Kei, which is in the chat, I believe. Then I did 6 months within this lab, at the end of which Alejandro Franco suggested me to continue as a PhD, to do manufacturing simulation. So here is the system I'm studying. So it's composed of active material, which are in red, carbon binder, which has been thoroughly spoke about in yellow, and then you have the electrolyte in purple in the image and in black in the video, and finally you have your separator and lithium foil. So the aim of my PhD is to match at first with experiments, and then to be able to predict performance only based on the mesostructure of the electrodes. However, it can be quite challenging because we want to apply this methodology in a 3 dimension by including also the carbon binder. So let's have a look at what was done in the literature before I started my PhD. So there was 2 main approaches. The first one was to implicitly consider this carbon binder phase through the electrolytes. So in fact, we will only represent the active material spherical particle and consider that the rest will be a mix of electrolyte and carbon binder particles. Or you have the opposite approach where you will merge your CBD with your active material and then just leave the electrolyte by itself. However, now there has been a growing interest in this consideration of CBD inside the 3D modeling. And it was also the case for one of the students of Scott Roberts, who published this paper in 2020. So one of the main struggle people faced during this implementation of CBD was, how can I mesh this multi-phase structure? So for those of you who doesn't know what's a mesh, I will try to explain it as the best I can. So the mesh, you can see it as how you will divide your system into smaller ones to describe it to an external software. So for instance, you need to implement the physics in this system. So you will divide your surface into triangles, as you can see here. And then you will divide your overall volume into tetrahedrons. And such tetrahedrons should match, obviously, your surface triangles. However, there's few subtleties when it comes to meshing. You can imagine meshing as trying to paint a man standing next to a mountain. If you pick a paintbrush which is too wide, it will be really quick to do the overall picture. However, the feature of the man will not be really well kept. His geometry will be like blurry. Whereas if you use a paintbrush which is too fine, you will have a proper definition of the man. However, it will take forever to finish the mountain. So for instance, here is the picture we would like to mesh. Like your man is here, enlarged in this little square. If you try with a fine mesh, so fine paintbrush, you will get that the man is well defined. However, the mountain has way too much precision, and it will take a lot of time to compute. Whereas if you use a wide paintbrush, you can see that your man is almost not recognizable. It's like almost nothing, but your mountain had not much, but enough details to retain the original image. So that's why we need an adaptive mesh, which will be able to capture the smaller scale geometry while not overloading your mesh with too much elements. So the challenge in this task is that we have multiple phases. For instance, at least we have active material, CBD, and electrolyte. However, there is a constraint that when you are meshing two different phases, they must match at their intersections, which means if you want to mesh an active material particle, which is like 10 microns of radius, and a CBD particle, which is like 1 microns of radius, the intersection of the two must have the same mesh. So it means that if you have a mesh which is finer for the CBD and coarser for the active material, at the intersection, the size should be the same. So obviously it was one of the main struggle. And especially in the battery lithium, the battery research field, because before recent years, as Scott Roberts said yesterday, the CBD was of little interest in the community. However, it was how this kind of problematics were already addressed in other fields, for instance, for the ceramic field, from this paper of 2014, where they did apply a technique which is called voxelization to capture all these different grains and orientation in their modeling. So what is this voxelization technique? So at first, you start with your input, which is segmented binary images. And then you apply this voxelization, which consists in first, you have your node generation. So basically, you will create a node network, which will be based on pixels. So for instance, each pixel will be a node in your network. And then you will create what we call a voxel, hence the name voxelization, which is based on each volumetric pixel. So it will be based on 8 different pixels. And once you have done your voxels, you will further divide them into tetrahedrons, so which will be called elements in the final mesh. So this generation is illustrated in this short video. And as you can see in this little here, for instance, if we focus on this tetrahedrons formed with those 4 nodes, here, 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 and here, you can see that all the nodes does not have the same color, which means they do not belong to the same phase. That's why we cannot stop at this element generation step. We should go further into the what we call the segmentation case, where you will further divide your tetrahedrons into even smaller tetrahedrons until you will have all your tetrahedrons which belong to only one phase. So in our case, either active material, CBD, or electrolyte. And then we'll come up with the output, which is obviously your volumetric mesh. So the benefit of this method is that it's based on really simple operations, which enable me to well optimize this process. So I could be able to generate, for instance, this 15 million elements mesh under 5 minutes, which is still powerful, but with a desktop computer of 32 gigabytes of RAM. So if for any, and it's like the average, it's well enough to have 15 million elements. It's way more than I'm using in my daily simulations. So it shows that it's really fast and efficient, even on desktop computers. You do not need like an amount of resource which is like on a server or a supercomputer to perform this algorithm. And that is why also I wanted to spare the people the struggle I went through for developing this algorithm by trying to share this app freely. It's not yet available, but we hope to make it soon available to everyone. And it will not require any MATLAB licenses. Anyone will be free to use it. So I would like now to present a bit more this interface, which I try to make it as user-friendly as possible. So at first, you have the importation of data. So you have 3 different types of data you can import. Either you import text files which have the coordinates of spheres, so the X, Y, Z coordinates of the center and the radius. Or you can also import 3D matrix in the native format of MATLAB, .mat. Or the most common one will be segmented images, either come from tomography or computed images, or whatever suits. Then you have this panel which allows you to have a 2D visualization of your structure and to provide also some information about it, like the pixels and the number of phases it detected. Then you have here the option for the meshing. So you have some helps, obviously, to detail a bit more what does each parameter. But for time's sake, I won't go into length into each one. But what's interesting is you can automatically generate mesh data about the mesh you just did, which will be converted into this text file where you have like information like the number of tetrahedrons, phases, the parameter you used for your generation, and also some observables such as the coverage, active material current collector, active material electrolyte, and so on. And finally, here is your panel where you can generate your mesh and then export it. You have several choices for the exportation. Either you choose to have a surface mesh, so either .stl or .pli, or you can try to import a volumetric mesh, so either in Nastran, or what I'm using, which is the COMSOL native format, COMSOL being the commercial software I'm using for my simulation. And I also added the choice to generate videos, because I think it looks good on presentation. So here's I applied it to tomography images with 90 FPS for a video length of 20 seconds, where you can see in red as before the active material, in yellow the CBD, and in dark the electrolyte. So now we'll try to do a quick live action demonstration of my algorithm. Hopefully everything will go according to plan. So first of all, I will try to demonstrate this importation of XYZ file, so with the coordinates and the radius of each particle. So at first I need to say which resolution I want my image to have. So here I'm saying I want each pixel to represent 1 micrometer. You will see that it's quite coarse, actually, this resolution. We can go for way lower, but for time's sake, I will do really coarse stuff with this app. So here you can see that has been successfully imported. You can go through your structure. So here in green you have your active material, in yellow your CBD, and in purple you have your electrolyte. So you can see it's really coarse. So it's like 26 by 26 by 61 pixels. So it's not really what you would expect for modeling. That's why when you can go to higher resolution. So here's the same images, but with 0.1 micrometer of resolution. So as you can see, it's way more what you would expect to have, like way more well-defined. Now you can try to mesh it. So here it's just precision. So I want my mesh to have. You can read through the help section if you want more information. So here you can see that the structure is being meshed at the moment. And you will see it's really fast. Also that the mesh will not be super fine, but you will see that even for my own use, it's the kind of resolution I'm using in my daily simulation, and it's sufficient for my own need actually. So here is the mesh you get. So as always, in red you have your active material, and in yellow your CBD. Here, for visualization's sake, I did not plot the electrolyte to visualize a bit better the structure. And you can also then import what is more maybe interesting, which is tomography images. So as you can see, it's really efficient. So if you look at the log here, it took around less than 1 minute, like 30 seconds to compute. And I'm not using a supercomputer. Also, it's true that it's like 32 gigabytes of RAM, but still it's not like the most computer you can find. So it can really be applied to every user. And I hope I make it like user-friendly, sorry. So it will be easy for you to use. So here is the tomographic data I imported. So in purple, I have to say that in purple I have my active material. Here in green I have my CBD, and in yellow I have my void. You need to say each time, because sometimes it might depend how you segment your images. So just to be sure, I implemented this panel. And we also try to generate the mesh. So here you can see that the images are really well defined because it's like quite big, 500, but it's basically a cube of 500 pixels of length. And you will still see that the meshing process is quite fast, hopefully. Yeah. You might argue that the mesh quality is not the best, but again, it's for time's sake. I'm not spending a couple of minutes waiting for the mesh to be done. Okay, so let's go back to the, yeah, everything is fine. Let's go back to presentation. So as a little sum up, here is the workflow of the of how we use Innov, which is the name of the algorithm of the app. So either you use file which says in where are the coordinates of your sphere, which comes from simulation based on physics from Theo and Alain, who presented earlier this week, which is here from so what we call CGMD, coarse-grained molecular dynamics, or it can come from tomography when you have to do this segmentation process, and that's just this step. We are doing it with Fiji and Weka, which is an add-on of Fiji. So from this, you can get a bunch of observables, which are always nice. For instance, the volumetric ratio, the interfacial surface area, or even the distribution of each phase along the height of the electrode. However, it's not the primary goal of Artistic to have observables. What we aim for is to do simulation and prediction. That's why then we move on thinking, how should we implement the CBD? What should be the physics we will apply? So we came up with 3 different hypotheses. The first one being that the CBD will be blocking for lithium ion, which means lithium ion will not be able to diffuse into the CBD. Then a partially open hypothesis where the lithium ion will be allowed to travel through CBD, but with an effective diffusion coefficient, which will be based on its tortuosity and microporosity, obviously. And then the fully open case, which basically consists as treating the CBD as electrolyte. The lithium ion can diffuse as fast as in the electrolyte, and they can also intercalate at the interface between active material and carbon binder. So obviously, the first assumption will highly underestimate the lithium transport, because we know from experimental point of view that we have microporosity, which allows transport of lithium ion. The second one is supposed to be the more realistic one, because the last will for sure overestimate the lithium ion transport. So let's see, here are the results when we applied it to 96.4 electrode of NMC, which was coming from CGMD simulation. So here is how I represented the results for each different hypothesis at 4 different C rates. So C over 20, 10, 5, and 0.8 C. And here, for clarity's sake, we displayed the evolution of the specific capacity with the different C rate. And as you can see, at first, when we apply low C rate, we obtain more or less the same specific capacity for each structure. However, as we increase this C rate, you see not dramatic, but the differences are, the gap is increasing between the 3 different hypotheses, with the blocking one being the less effective compared to the fully open. So we can explain this through very basic thinking, because when you apply a really low C rate, we would expect this system to be thermodynamically driven, because it has time to equilibrate and to reach the thermodynamical equilibrium. However, when you apply a high C rate, you would expect the kinetic to play a major role, because then it will be all about how fast lithium and electron can go through your electrode. So one of the best thing about modeling is that you can have access to all these different observables at each time in your system once you have your simulation done. Here is a map of lithium concentration in the solid and in the CBD at different discharge time for each different hypothesis. So we will have a closer look at the end of discharge because that's where the differences are the most dramatic. So here are for the three different hypotheses: blocking CBD, partially open CBD, and fully open CBD. So as you can see, the CBD here, when it's blocking, the concentration is equal to 0, whereas it's around 1.5 for the fully open and partially open case. So if we focus on this given active material particle, you can see that in the blocking case, it's the distribution of lithium is really inhomogeneous, whereas for the fully open case, you can see a perfectly homogenized concentration. And this is all due to this CBD here, which is preventing the lithium ion to access the active material and to intercalate at its interface. So that's why it's really a powerful tool, because it can explain macroscopic observables such as specific capacities, thanks to mesoscale effect of the morphology of CBD, because here the CBD will prevent the access to the active material particles, and then you will have a gradient of concentration, which will lead to higher polarization throughout your electrodes, and then less capacity in the end. So a quick sum up about this CBD physics. We show that this explicit conservation of CBD is possible without having like a supercomputer or even a server, because all the simulations were performed on my computer, so 32 gigabyte computer. Then we believe that the partially open hypothesis is the one that will be implemented for higher precision. We shouldn't consider the CBD to be blocking for the electrolyte. And then from our workflow, we were able to show that we can explain, for instance, how the difference in capacities because of the mesoscopic effect of CBD on the active material particles. So then we got interested into another technique, electrochemical technique, which is called the galvanostatic intermittent titration technique. So basically it's easy. You apply a pulse of, you can either apply a pulse of current or of voltage, sorry. In our case, it's voltage. So it's displayed in red, dotted red here. And then you will look at the response in current. No, sorry, you apply current, and then you will see the response in potential. So potential here is in the full blue line. And given its response, which will be into delta ET or delta ES, you will be able to extract with this formula a diffusion coefficient of lithium throughout your active material. However, when we look a bit further into the literature, we have noticed that there was a wide dispersion of reported values for here the NMC 111, and it's not the gap, the range of year is not like huge. It's on 6 years. There has been 4 orders of magnitude almost between the highest and the lowest diffusion coefficient reported. So we ask ourselves if it was because, if the discrepancy in reported values was because of the hypothesis behind this formula. So what we did is we applied this given workflow. We did an experimental GITT from which we were able to extract this diffusion coefficient thanks to the formula. And then we said, okay, now that we have the experimental one, we will use that as an input for our simulation. So we will say, okay, we will know precisely we'll be controlling precisely what the diffusion coefficient is. And then we will run a simulated GITT and extract again this diffusion coefficient. And if it's not the same, it will mean that there is some hypotheses which are wrong to be assumed in this formula. So here is the different results we got. So once again, we applied these 3 hypotheses workflow: blocking, partially open, and fully open. So as you can see here, this OCD curve which will be extracted from experimental and modeling, is quite in accordance with each other, in agreement with each other, I would say. But however, when you look at the extracted lithium ion coefficient, you see there's a factor 5 difference between the two, between the experimental one and the simulated one, which means there is an issue with the formula, obviously. But what's more is like when you see it goes from blocking, partially open, and fully open, this in increasing values of diffusion coefficient, because this fully open case is the one closer to the hypothetical system where the equation was derived from. So at first we had a critical view over our simulation, and we figured maybe it's not in agreement, experimental and simulation, because we did not wait long enough before having the second pulse coming. So we tried to plot this lithium ion concentration throughout the cell at each given time. And as you can see, we got a staircase shape for this plot. And this staircase shape means that at some point, for instance, if we look here, the pulse stopped. And since this concentration does not evolve during this time, it means it has reached this equilibrium. And then the next pulse was applied, and then it has time again to reach a stable concentration, and so on and so on. So we make sure that this waiting period was long enough in between each pulse. You can also visualize it maybe a bit better in video. Right here you have this concentration plotted. And as you can see, there is a yellow isolated point here, which is due to an active material particle being isolated, prevented. There was no lithium ions that could go through. And then you can also see here, maybe I will show at the beginning, it's more clear. Then you have stronger gradients in bigger particles. Here, for instance, you can see it takes more time. You can see that it's not homogeneous, the concentration inside these big particles. So here, there is a heterogeneity due to these big active material particles or due to isolated ones. But it will be more clear, I think, in 2D view. So here, sorry. Here is a slice at the given point of the GITT simulation for each different hypothesis, where you can see that there is a dispersion in particle size radius. For instance, this given particle here is obviously smaller than this big one here, and it leads to higher heterogeneity in the bigger particle, because you can see that this big size particle is the one where there is a steeper gradient of concentration, whereas overall it's more or less homogeneous. Moreover, the environment of the active material particle plays also a huge role. For instance, once again, the CBD morphology. Here there is several snapshots of two different particles at different times of the pulse, before, in the middle, and at the end. So here you see before the pulse, as we said earlier, the concentration is homogeneous, so it's nice. At the middle, you have a gradient forming, and at the end, it equilibrates more or less. And due to this CBD preventing access of lithium, of the intercalation, you can see that in this particle, which is like not fully covered with electrolyte, you have a stronger gradient than in this particle, which is fully in contact with electrolyte. So which led us to think that this location of CBD was also a source of heterogeneity in our system. So more or less, we've shown that these two are sources of heterogeneity, and these heterogeneities are going to lead to, the main source of deviation from this ideal case where the formula was derived. So to sum up, we've seen that there was a discrepancy of reported values for diffusion coefficient. In our case, it was NMC 111 in the literature. So this equation was relying on hypotheses such as an infinite charge transfer or uniform particle size distribution. But we've seen that throughout, thanks to our simulation, we will provide for the first time insight on why it's not obvious, not all the time true, and we should be wary when you are using such equation, because the particle size distribution will have a huge impact on the distribution of your lithium concentration, and then on your gradient, and then which will have an impact on your diffusion coefficient, and also the environment of your active material, because one of the hypotheses is that your active material particle is fully exposed to electrolyte, but in real electrode, obviously it's not the case. So to conclude, CBD modeling is right now a hot topic, and really recently there has been a really nice paper coming out in Nature Communication, which was also doing kind of the same workflow, which is importing it to COMSOL, this time with an amazing resolution. They were using 30 million elements and also performing a really nice and thorough electrodes and capacity simulation. Also, we will be proud to really soon release our first version of the Innov app, which will be available to everyone. So we hope we will be numerous to use it, because it's like an easy and free approach, because most of the meshing app software are commercial ones, whereas it's not mandatory here to pay for such a task. And then we have shown that this Innov app can be applied for electrochemical modelization. For instance, here a discharge and GITT application, and we were able to obtain some, I think, nice insight on what is happening and how the morphology of CBD will impact the macroscopic response of your battery. And then as perspective, I would like to update regularly this Innov app, because right now it's like a simplified one. I have something more sophisticated, but it's not ready yet to be released. And also I would like to simulate a full cycle of charge and discharge, which is something that really lacks in the literature at the moment because of the difficulty to inverse the current, I think. And finally, we'd like to model a full cell, but for sure it will apply to make some sacrifice in terms of resolution on the mesh. Otherwise, the modelization will be too computationally expensive. So I would like to thank all the artistics team, which I'm proud to be part of. And now we'll have some time, I think, to answer to some questions.
Thank you very much, Mehdi, for a great presentation. So yes, it's time to answer questions. So you have many questions, several questions, question list.
Yeah, when those
so I read a comment from Sam Cooper saying, "So brave of doing a live software demonstration, extremely impressive."
No, yeah,
Thanks, Sam.
I was a bit scary at first. So does Innov work with Octave as well as MATLAB? I did not try with Octave. I know the two languages are really alike, but I've only tried it on MATLAB, and I'm guessing it won't work. But the app we will release will be a standalone application. You won't need to have a MATLAB or an Octave version or license to work, to operate. You will be just download, install, and it will be working fine. But I don't think it will work with Octave as it is. So I'm just wondering if it can be used for fine and coarse meshing. I'm not sure I'm understanding right your question, but the thing is, you can control. I will maybe get back to this app. You can see. You can control more or less the precision of your mesh by this precision parameter. For instance, here I do a really coarse mesh by having a really huge precision, a huge number of precision parameters, which will in the end be really coarse. As you can see here, it was really fast, but the output mesh is horrible, obviously. So that's how we can play from a coarse mesh to a finer one. It's with this parameter, which enables you to tune it to what you really want. If you want to have like 100 millions of elements in your mesh, it's possible. It will just take a bit more time, but it's possible. But you can also generate like few hundred of thousands elements as easily just by tuning this precision parameter. And as you can see, when you decrease this parameter, it's way more satisfying, the output to mesh.
There is a question below that you start to answer in the text, but yes.
Yeah, okay.
From Haja Chandran.
So can enough be used for all solid composites, for material without liquid in it? The thing is, it can even be used outside of the battery field. It's like the input is just images or matrix or spheres coordinates. It's obviously tuned for battery, because when you export your mesh into the COMSOL native format, sorry, I've done some mesh selection. So it means when you will open your mesh into COMSOL, you will directly have access to, for instance, all these active material particle domain into one given selection. So you won't have to manually select each one, which obviously is impossible when you are dealing with thousands of elements. So obviously I did some selections like that, which are tuned for the battery field, but it's not limited to that. You can have for mechanics, whatever images, you can even have some, if you want to do some rendering 3D, you can import like images of a sliced STL and generate it in 3D. It's really up to you. It's really versatile, I guess, this algorithm. I think your hypothesis of CBD being partially open to allow lithium plus transport confirms with the talk of Dr. Scott Roberts, who showed the process. Yeah, exactly. I was kind of pleased to see that we were going in the same direction. However, I think he allows this intercalation at the CBD and actual material phase. Ourselves, we for now sticking with this, preventing this intercalation from happening. But yeah, we are going more or less in the same direction, which is encouraging. So what are the current intensity associated to your different C rates? So I do not remember exactly, because the thing is, we apply a C rate, which is based on then the overall capacity of our cells. And we apply this C rate, this current, at the current collector phase, obviously. And then it depends, and this interface evolves with a different structure. For instance, from if you have a more packed structure, you will have better contact between your electrode and your current collector. So you will have a lower flux. If you are in the case of an uncalendared electrodes, where you have lesser contact in between your current collector and electrode. So it really depends on the contact you have at your current collector. But maybe I can guess that it goes really high for instance, 0.8 C. It can go maybe to 200 ampere per meter square, I guess. But it's just a magnitude. I mean, it's not a precise number. So, but it really depends on the structure you are studying. So the C rate for JTT was the same that we used for the experimental one, which was C/50, which was applied for 30 minutes. So I have a question. Have you ever used for mesh for FEM software such as COMSOL or Abacus? I mean, maybe I've not been clear enough, but I'm using this Innov app to import my meshes into COMSOL. So yeah, I definitely did. Abacus I never tried, because we are only working on COMSOL in this group. But obviously, it's actually it was tuned to work only with COMSOL, this app. My needs were to import into COMSOL. So it respects this, because COMSOL has some specification you should follow for its native format, and it respects it 100%. So there is no bugs when you are importing your data. lot of questions. So in case of generation of conformal meshes for the structures resulting from the CGMD simulation, how are the contacts between CBD and active material realized? So from this X, Y, and Z file where you have all the coordinates of your particles, what I did is I generate then the 2D images by giving priority to the active material. So when the active material and CBD were overlapping, the active material had the priority. So it was like the CBD basically disappeared where the active material were. So that's how I dealt with this overlapping of the two, if there were some. So can you share the reference paper used for generating meshes from images? So yeah, if you like, I can send you, if you drop me your email, I can send it to you. It's like, it's based on an algorithm which was published in the before the 90s, 87. I don't remember really the date, but it's quite old for science. And yeah, the algorithm is quite simple. That's why I chose to try to implement it. By itself, it's simple, but the implementation into an algorithm, the coding software, it's something else. But the algorithm itself, it's quite simple. So if you want, I can send it to you. So is it possible to use mesh in OpenFOAM, or is it just for using console? That's why actually I implemented this, as you can see here. If I save mesh, you can choose here from MPH text, which is the console native file, or you can have BDF, which is Nastran file, which is a format which was developed by NASA in the 70s. I think it's quite worldwide used. So it's possible, it should be possible to import, I guess, in approximately almost all the software. I've never used OpenFOAM before, so I do not know what format they are allowing, but I'm pretty confident it should work with Nastran. So I'm curious whether enough can regulate the number of elements in the mesh. So it's not, it will be nice, but it's not something I can control. It's not an input parameter. It's more like an output observable, I would say. But since you can have access to this number through the text file that automatically is generated when you click on mesh data, if I can go back, you can do like an iterative meshing process to reach the amount of elements you want, thanks to this output, which is here. Here you can have access to the number of tetrahedrons you have once you generate your images, your mesh, sorry. So you can do an iterative process to find the precision you need to have the number of tetrahedrons you want, but it's not something I control beforehand.
There are more questions in the top from Fedeke.
Yeah. So during lithium of lithium, there is a phase change on the electrode with entropy. Are planning to consider this into your model? Right now, we do not consider phase change in our model. That's why we are currently trying to also move to graphite simulation, where we might have this issue of phase transition. But here we do not really take it into account, because in a 3D model, either you will do through parameters which will evolve as a function of your lithium state, but it's really tricky to have a dynamic mesh in 3D to account for this phase change. But I don't think it's something we want to look into, because we have other stuff which are more pressing. But obviously, if you want to aim for precision's sake, and if you want to apply it to, for instance, LFP material, for sure you should take that into account. But in our case, we do not for the moment. So So is it possible to create different meshes for different phases? Let's say give more precision to a specific part of the system. So basically that's what I was explaining in the previous slide. It's one of the main constraints we are dealing with is the fact that the mesh should match at the intersection of the different phases here. Because if, for instance, you want here it's your CBD and here it's your active material particle, obviously you would like to have a finer mesh for your CBD since it's way smaller and the scale is smaller. But the thing is, at the intersection of the two, if they are like in contact, you should have the same mesh. So the element size should be the same at the interface. So that's not something Innov can do. It's doing basically that at a small scale because it's further divide each tetrahedrons until you have each tetrahedrons belonging to one phase. So if you give a close look to the intersection, for instance, here, you can see it recognizes a two phase, the white and the green. So in the bulk, you have bigger elements, but when you go to the surface, at the intersection, you can see that the element size is decreasing. So that's what Innov can do. However, it cannot like mesh two different phases with different resolution and then merge them. I think the software that the team who published in Nature Communication used commercial software for meshing was able to do that, but mine is not.
I don't know if the attendees recognize this is FFF is the French Federation of Football, with the two stars of the World Cup. So you understood that Mehdi is French.
So is there any question in the chat? No.
You have some comments in the chat, I think from Hilda, talking about effective medium models. There is three comments.
So it's very exciting to see that your results can corroborate hypotheses of effective medium models. So I'm not really familiar with those models, so I won't comment on that, but thanks. And if you want to collaborate, obviously, we're open.
Okay.
Well, time is up.
A lot of questions. Yes, thank you very much, Mehdi, for a great presentation. And
thank you for your.
I agree with the comments. Is that it was very brave. I mean, to decide to make the demonstration live, and yeah, it's great. It's great.
It shows how confident I am in my app. Yeah.
No, but actually, yes, it's a very, very strong app, and it's really very useful for the work being carried out in the artistic project, because Mehdi is really in the end of this simulation chain between different simulation techniques. And the difficulty was how to import these complex structures coming from CGMD and DM simulations into a performance simulator, right? And Innov is a critical step. I mean, it's critical part of the project because of that. It allows importing any kind of structure, whatever the complexity is, in a simulator that then we can plug physics, I mean, to describe electrochemistry and so on. Thanks, Mehdi, for a great job.